So, recording. Okay, so what happened is that when we discussed that last time, that, how the different, like the idea of atoms or the matter and light being, like the light and the matter, like the light comes from the matter. Initially, they thought that the matter and the light were two separate things. But when Max Planck, when he did his experiments, which is the black body radiation experiments, these are also called the incandescence experiment, in which he took the matters, like the rocks made up of just a pure metal, just a pure substances, like which contains only the one type of particles, and he put them in the oven. He found that the light was emitted, and this oven was a pitch dark oven, so no light was coming from outside anywhere. So when this happens is that the light is coming from these particles and from this matter, and they found that different colors of light were emitted at different temperatures. So now comes the question that where, that means the matter can produce light, but where is that light coming from? So we discussed that last time, that when the electrons, they acquire the heat, or they acquire the energy, they get excited, and they jump from a lower energy state to a higher energy, or even higher energy to a lower energy. And when they do, there is some emission of light. And this emission of light, this light itself has wavelength, has frequency. That means it has energy. So using that color of light, they were able to give a specific value to the energy levels. So yes, we all know that the nucleus is in the center of the atom, and all around it are the energy levels. So nucleus is the center. That's fine. That was already Chadwick, I think, discovered the nucleus. And then J.J. Thomson, he found out that, okay, yes, there are positively charged particles called the protons. And then there are neutrons, which are, neutral. And the main bulk of the atom is because of that. But all around the atoms, Bohr said that all around the nucleus are these energy levels. All these are also called the shells, and he called them orbits actually. So these energy levels, when the electron jumped from these energy levels, from a lower to higher or higher to lower, then these energy levels, they were able to give some value, some number, some kind of, like they were able to quantify these. And this quantification, actually, this is E1, E2, E3. So this led them that, yeah, this guy is of a very high energy, that outermost energy level, outermost energy level. And this energy level is also called the valence shell. So this is the outermost energy level is also called the outermost shell. And this is the valence shell. Let me just put it here as valence shell. And the electrons are found in these energy levels. Now, how many electrons are found and where exactly are they located? Now, that was where Schrödinger came up with his wave equation. So how many electrons and where exactly, where are electrons located? And fine, we understand that they have a negative charge, but what do they look like? What do electrons look like? Okay, so all this information came through Schrödinger's wave equation, and this is what he studied. But before that, let's look at de Broglie's principle. De Broglie, D-B-R-O-G-L-I-E, de Broglie principle is, he, like we're talking about the quantification of these energy levels. So he said that we understand, in his mind, the electrons, like remember, they were all working on electrons, basically focusing on the electrons. And of course, the energy levels, they were able to quantify, but now we are just focusing on the electrons. So what do the electrons look like? So de Broglie said, oh, they look like waves. They are like this. This is how they look like. So This is de Broglie's, So in the waves, so they are just circular waves. Electrons are circular waves, and these waves are found around the nucleus. And what is the energy of these waves or energy of these electrons? And we know it is equal to mc square, which is the basic energy given by this is the energy that is given by Einstein's wave equation, Einstein's equation. Okay, so this, when we use, if these electrons are circular, they're waves, that means they are moving, right? And if they are moving, that means they have energy, kinetic energy. Anything that moves has a kinetic energy, energy of motion, right? And that energy of motion is this here. This is the speed of light. It's not just the speed of light, the speed of any wave, So this is the speed. So that means if all this is there, that means the electrons must be having a mass. You see that? So this is how things get related in chemistry or in science, through the formulas. So we know it has a speed, we know it is moving, so it has to have a mass. Now, what is the mass of that electron? So that leads to another, speculation. So a lot of mathematics goes into here, but we also know from the incandescence experiments and through other equations, Bohr's model, that H is the Planck's constant, Hc over lambda. This is another relationship of energy. Okay, and now we are trying to determine what is the mass of that proton. How do we determine the mass of the proton? So just speed, and this is not enough. So we need to know more. So how do we know the mass of a photon? Or in other words, so basically electrons, electrons, because they are moving, all that, so they are equal to, he looked at them as photons. So that was his thought. So mass of photon. So in other words, how do you quantify that? How do you get that? So the mass of photon is equal to, using the E, is equal to mc square. When you rearrange this, then you get E over c square is equal to m. So the mass of photon is E, the energy of the photon, over the speed with which it moves. So this is one piece, but that's not sufficient either, because we are using light as our, there's no way, it's not the technical era. Remember that. It's not a technical era where you have a lot of advancement, a lot of machinery, a lot of technology is there, a lot of, equipment is there to put things, to weigh things or measure things, and computers were obviously not there. So what else? So like I said, they were always using light as like a reference, to measure things or to figure things out. So that means if we are bringing light, that means we need to bring wavelength. Remember last time we talked about it, the light moves, light is made up of photons, and these photons are moving as waves. And these photons, when they are moving as waves, then they have the wavelength, right? And they also have the frequency. So wavelength and frequency is there. So we need to bring that in order to understand the mass of the photon. And so how do we get that? Okay, so you are going to bring this, another equation that we know, energy is equal to Hc over lambda. So put this here, energy is equal to Hc over lambda. This is another relationship. So instead of now, you can just put this and this energy in the mass of the photon. So replace that, mass of the photon is equal to Hc over Hc over lambda. I'm going to just put it here because he's just putting the value for E, which is Hc over lambda upon c square, right? So he's just basically putting it here, the value of energy. So then again, rearrangement of this is going to give you the mass of a photon is equal to H over lambda C. That means now we have the wavelength, which comes through the color of light, wavelength, and the speed. C is the speed of light. So C is the speed, and H is this is the wavelength, and wavelength, and then then wavelength, and then H is the Planck's constant, and that has a value, Planck's constant. Okay, now we will see that when you rearrange this, so wavelength is equal to H over MC. So this whole equation can be rearranged. This piece right here can be rearranged as if you need to find a wavelength, then you can get that also. So this is your, this is going to be your one equation that, you can put, and you can just put things here and put the values here, and you can get the data. So I'm going to do some of the problems later because we have a lot of theory to cover. And let's look at now, how did Schrodinger come up with his wave equation? Schrodinger's. So we are not looking again into the derivation or the full-fledged Schrodinger's equation. That's like in physics, you study that. But in Schrodinger's, I get the spelling right, waves. So in other words, how did he came up with that? Okay, we have to, like I said, he used guitar to understand the behavior of waves. So this is a good part that de Broglie came up with, that like, oh, the electrons are moving in a circular fashion around the nucleus, but all this is the, and this is what it looks like. I mean, it is circular, but still it's a wavy, circular waves. So that was a very good insight he gave. And so that led Schrodinger to study the waves. And so he said, okay, waves, we understand the waves. Where do you find the waves? Waves are found in water, right? Water, like water bodies, or waves are found in like air, or even musical instruments. So these musical instruments, guitar, so there are two types. Something he studied. Look at this very powerful thing. Look at this now. Okay. When the two strings of the guitar work together, okay, so this is one string of guitar, like when you pluck the string of the guitar. So this is one string and this is the other string. So this is in sync and beautiful music is produced. Okay, so when the waves work together, so these are the waves that are in phase. So this is the in phase waves, and we also call is when these waves are in synchronous. Synchronous means like work at the same time, synchronous waves. Okay, so when these waves are in synchronous, what do you get? When the musical instruments, when these work together, what are you going to get? Beautiful sound, and it is going to be a music actually. So they intensify. Two waves, two strings working together, they intensify, and a bigger sound is produced, and it's musical sound because they are synchronized. Okay, so a musical sound is produced. So this is called constructive interference. Constructive. So when we constructive means you are creating music. So this is called interference. So this is one piece, very important. That makes sense. Okay, but the problem is, what happens if the musical instrument, one wave is coming this way, okay, coming in this direction, and the other one is coming in the opposite direction. What happens then? Yeah, what happens then? Very good. So yeah, you would still get some sound because they're still going to be, because they are meeting at some point, right? They're still meeting a little bit somewhere, but it's not going to be as nice. And so it's going to be a flat sound. So this is called the destructive interference. Destructive, DESTRUCTIV, destructive interference. So when there is a constructive interference, you get music. And when there is a destructive interference, it's nothing but cacophony. Like just, it hurts our ears also, right? Or it may be just a dead sound. So anyways, so the waves, when they meet, you can also write this here, that the waves are meeting out of phase, out of phase. And these out of phase waves, they are non-synchronous or asynchronous. Maybe it's asynchronous. So that's where that's how you see your names of your classroom. The online classrooms are also synchronous classes, meet at the same time when, when the Zoom meeting is open, when the class is scheduled. Asynchronous, you can meet whenever you want to see, you don't even meet. So those type of things. So in this case, he studied this, a very powerful observation here. Okay, so he said, okay, wait 1 second. He observed another things. So look at this. When you pluck a wave, try to do that. You guys can see that when you pluck, if you have a musical instrument at home, then you would see in a guitar how these waves, how these strings are attached. So they are attached from two ends, and then all you need to do is just pluck the string. So you pluck it and it moves like this, and then it moves like this, right? When you pluck you pluck the string, okay, of the guitar. So you would see it moves either up or it moves down, but same intensity, like the same distance is the same. So one piece, okay, fine. Next is, let's look at this piece. One, if you have another type of instrument where there are more places where the strings are attached. So this string is, if the string is attached to this is the bass or whatever. So these are the little hooks. Now here is one string, and if you pluck this string here, and then it's going to move like this, right? So these are some other musical instruments where the waves are, where the strings are attached at different points. So there are 3 places. So here there are 2 nodes. There are 2 nodes here. There, in this case, there are 3 nodes. So when you pluck the string, you see it only goes 2 places. So again, it will move up and it will move down, same. Now look at another instrument in which there is 1, 2, 3, 4. And these strings that are attached are, if you pluck it, it moves here, and then it moves in the opposite direction, same. This guy moves here and comes back, same. That moves here and then it moves same. So what we see here is that 1, 2, 3, 4. There are 4 nodes or 4 sites where those strings are attached. So 4 nodes. So obviously, if you look at it, sound is also an energy. Music is sound, and that is also an energy. So here you can see how the music is going to change. The music changes. If there are just, in the first case, the music is different. You agree to that? I mean, just looking at the diagrams, you can tell. In the second case, the sound is going to be different. In the third case, the sound is going to be very different. So that means that the more nodes there are, it's a different type of music. Based on that, so many different, string instruments are there based on their quality of, the music they can produce. So anyway, so these nodes have a very powerful thing, like a insight he got from the music that, okay, now look here. This part right here, where we hear the music here, anywhere here. This is where the probability of finding the electrons would be. So this is like he is connecting this instrument, what he's doing here, with the electrons in the atom. So the structure of atom, this is very fine. Structure of atom now is being studied by understanding the music produced by the strings in the stringed instrument. And we are trying to understand the behavior of the electrons. We are trying to understand what do the electrons look like, where are they located, and how many electrons are present in one part, where in the electrons, where are they present, those things, and how many, all those things. So now we are trying to find, okay, locating the electrons. So where are the electrons? The probability of finding the electrons is the maximum in that yellow area that I highlighted, but same is the case here. The electrons can be found here. If this was the structure of atom outside the nucleus, where the electrons are found at the energy levels, then the electrons can be found here, or electrons can be found here. Electrons can be found here, 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 here. Okay, so these are the places where the electrons are found, but it's a guarantee that when this spot, the electrons are never going to be found. You do not see when the string is plugged, no music is produced. So these places where the nodes are, we are guaranteed 100% sure that the electrons are not present here. So as far as those spots where the electrons are present, the sound is being produced, and this is a reality also. Actually, I'm going to just write this down here, that if you guys get a chance, you guys must go to the university, if you guys can get a chance. I know many of you are taking transfer and so forth. So University of Santa Barbara. University of Santa Barbara, they have allosphere. University of Santa Barbara, like I said, now, of course, we are very, very advanced. What we're talking about is the era where, nothing was there pretty much. Like the science was just evolving. So anyways, University of Santa Barbara has allosphere, ALLOSPHERE, allosphere. So here, these are like, just like you have these, what are these called? The microscopes, right? But thousands, like several thousand, I don't even know how many. So I'm just going to put there several thousands magnification. Just like you magnify, under microscope, you see the cells, the structure of the cells. You can see inside a cell, you can see the nucleus, you can see the Golgi bodies, you can see the mitochondria, right? You see those things. So similarly, what they have done is they've taken like the same technology, like the same thing that you put like in the, what are these called? Telescopes. Telescopes is all the same principle. So you can see very far off objects, like very close. You can see the stars and the galaxies, all those things on the telescope. So same thing here. And you guys, if you get a chance, you must see this place, or I'll show you a video also. In this case, they magnify the atoms, the molecules. Okay, and then what do they do there? You can actually hear the electrons talk to each other. The electrons of hydrogen talking to oxygen. And it's beautiful music. They talk in a very musical way, So when they move and they form bonds and all, it's just, you can just sit there and you can just go into some kind of trance. It is so beautiful. So anyways, so nodes are those places, 100% we know, where electrons can never be found. So at least we know one thing, that electrons are never going to be present in the can never be found. So the sound related to energy and that energy location of the electrons, and that is all this yellow region. Okay, so this is one piece. Next is, okay, now moving very fast forward, which, like I said, we are not doing any kind of like derivation. So we are just going to look at that. Schrodinger said, okay, in our world, there are 3 dimensions. What are those 3 dimensions? Our world is 3-dimensional world. Our reality is 3-dimensional. What is that? What are the 3 dimensions? Come on, guys. Very good. Very good. So height, how high, H-E-I-G-H-T, how height a substance is, right? How flat, or in other words, more like, instead of height, let's put it here, horizontal. Everything is flat, right? For us, we place the things and, you know, they're stationary, they stay like horizontal, vertical, how far things, you know, we look at the rooms, the walls, all those. So that's vertical, the flat surfaces, the horizontal, and then diagonal. How deep? So length, width, and height, diagonal. Okay, so this is our world. We live in 3D. Our world is 3D. Do you know there are more dimensions also? Do you guys know? No? More dimensions also exist. 4 dimension, 5 dimensions, 6 dimensions. But the thing is that 11 dimensions have been identified, but that's beyond our reality. Those are like, okay, this is just a little bit, might sound a little bit off track, but you know, because the 4th dimension has been identified, because they did this experiment a long time back. It's been like about 10 years now, and this was done in Italy. They were bombarding neutrinos, you know, neutral, right? Small charge, no charge, small particles. They were bombarding, and they were trying to see what happens if an object travels with the speed of light, because everything here is traveling less than the speed of light. But if everything is going beyond the speed of light, what happens? Can you surpass it? And if that happens, then, or even if something is traveling at the speed of light, that is the thing they were determining. But what they were found was that the neutrinos traveled faster than the speed of light. So that led to the discovery of the 4th dimension, that the 4th dimension, that there's no way that if you are in this 3D, everything is, you know, measured in reference to the speed of light in 3D. So that means the neutrinos crossed and went to the 4th dimension. That is why they were able to go faster than the speed of light. So that is why now we are looking at, you know, these type of new teletransportation. This is a new thing that they are working on. Teletransportation and like, can you like, you know, like this is a new research they're working on. Anyways, trying to figure out all these different what other dimensions are present. But anyways, that's beyond. So look at this now. So when you do these graphs, right? You guys do the graphs, right? Length, width, and height. So X, Y, and Z. This is horizontal and vertical, horizontal, vertical, and diagonal. Okay, so we have our world, everything exists in these 3D. Okay, so with that said, he said, okay, the electrons have to be present in 3D only. They can't be like in 4D, 5D, 6D. Electrons have to be present longitudinally, right? Vertically, horizontally, or diagonally. So we can only see the electrons in these 3 like sides. And then another thing he came up with was WH psi is equal to E psi. Okay. This is called PSI. This is a Greek symbol. And this is the wave function. Wave function. Now we are like all the all the functions of the wave. He did like a lot of work on the waves, more work. This is a simple stuff we talked about in 3D. And so all those are bunched up together in one relationship, in one. That is the psi. So what does E stands for? E is the total energy of the atom. So energy of the atom, energy of the atom, or energy of the, basically the energy of the electron, energy of the electron and the waves, they are interrelated. So that's one piece we come to know. Then what is this H? H with this little, thing over here on top, I don't know what that's called, but this is all the set of mathematical operators. Now we, like I said, we are not going into those details here, but just keep that, like if all the plus, minus, multiplications, divisions, whatever, all these operations that you used to figure out the energy of the electron, where it is located outside the nucleus, then all the math piece all in one place, and that one place is this guy, H. So these are also called the Hamiltonian operators. Hamiltonian, T-O-N-I-A-N, Hamiltonian operators. So we are not, looking into like the details, but what are we looking at? His main thing was, okay, he said wave function. What is that wave function? What do you mean by wave function? So he's saying that the specific wave function is called the orbital. That is where the electron is found. Specific wave function, very specific to every single electron. I mean, remarkable, really, really remarkable discovery of his. But its specific wave function, sorry, not functional, its function, that is called orbital. Every electron is associated with an orbital. And now what is orbital? Okay, orbital, that's where Heisenberg, so both these guys worked together. Schrodinger did a lot of math work, but Heisenberg also did work with him. And I think Heisenberg was Austrian, and I don't know, Schrodinger was also Austrian or German, or one of them was, I don't know. Okay, anyways, doesn't matter. Okay, so Heisenberg said uncertainty. He came up with his uncertainty principle. And that is that we know that the electrons are present outside the nucleus. Yes, we know electrons are present at a certain distance from the nucleus. That's also correct. We also know that the electrons are associated with some amount of energy. That is also correct. But where are these electrons located? They are present in the orbitals. That is also fine. But he said it is hard to determine the exact location of the electrons. The orbital is that spot where the probability of finding the electron is maximum. Orbital is that spot, like that location around the nucleus in the energy levels. So location in energy levels, outside the nucleus, where, now very important, probability. We can only be, we can, like you say, probable is like, yeah, if and but, those type of thing. Probability of finding the electrons is maximum. So if you're looking for the electrons, if you're looking for people, if you're trying to find someone, where do you see them the most? If you were to find a friend or a human being, where would you locate them? Where would you find them? Where? Tell me. Every human being. Where do you? Dogs, cats, birds, everyone. What is that common thing every living being has? I mean, except the plants and plants, I don't know. But where heat, yeah? No, in the earth is fine, but where on the earth? Where?
Everywhere,
Okay, leave that. Okay, let's say somebody's a criminal. Okay, where do you find them? Like if the police were to go search for them, where would they go first? Say that again. Come on, guys, think.
Their home or
Home, right? Like that's what I'm saying. Dogs, no matter what, like they love their little spot or little bed or whatever it is. The animals, the birds, you know, everybody, their home is the main thing. Even the homeless people, right? We say it's a homeless people, but they also have a little spot, you know, it could be a camp or it could be whatever, something makeshift they've done. That's their home, right? So home is for every human being, every living being. Home comes, home is where we find them. So orbitals are what? The homes of the electrons. Okay, so orbitals are homes. Specifically, not just a home, it is actually the room where electrons can be found. Now, both of them did not say, okay, de Broglie was wrong. De Broglie also used a whole bunch of math to prove that, oh, they are existing like waves. So they said, now mathematics, see, here's the thing, math is such a pure science. You cannot, like, you can prove a lot of things just by math. That's the thing with the math. So math, you know, you can prove whatever. So de Broglie has already proved that they exist as waves. And here they're saying no, but they also have a mass. So there has to be like, fine, we understand they have energy and they have a charge and all that. But then they came up to a common understanding or whatever their, you know, research was. They said that, okay, Heisenberg said they exist, the electrons exist as waves and electron exist as particles. So the electrons can exist both. Wave particle nature of electrons. So these are small waves that are found in the orbital, and that orbital is that region in space. It's a location in the energy level outside the nucleus where probability of finding the electrons is maximum. Okay, so electrons are existing as waves and particles, but it is not possible for us to say, like, at one point of time, they're going to be a wave, or at what point of time they're going to be a particle. That we don't know. We can't say for sure this is existing at like, you know, at this time when you're looking at the atom, it's existing as the electron is existing as a wave. No. So that piece is uncertain, whether it exists as a wave, whether it exists as a particle, but we know they exist both. Both of them is true. And that makes, you know, logically, if you look at it here is the nucleus, and the nucleus has a positive charge, and all around the nucleus are these energy levels. This is one energy level. This is another energy level. And by the way, this is a 2D diagram of electrons, of the atom. So anyways, and here is this electron negatively charged. Here is this electron negatively. If it is existing as a particle, what is going to happen? There is negative and positive. There is attraction. There is attraction between the negative and the positive. So these electrons, there's something called nuclear pull, which we will study this. So this nucleus is going to pull these electrons very easily. So the only way they can survive the nuclear pull is if they exist as waves. Then the nucleus can't do much. Then it has the attraction, but it can't pull. But if it's in a particulate form, then it just sucks that. It's easy to look. See, it's easy to locate a particle versus a wave. Wave is like, motion comes into play. Particle, it's easy to, suck it. So there is attraction, but nuclear pull, the electrons are, remember, they also said, let's look at it here. Let's write this down, that the electrons are existing as waves and particles. Next is that the electrons have a negative charge, and this negative charge is what they are attracted to the nucleus. So the nuclear pull, put this here, 4, 5. Okay, so the electrons are attracted or pulled, rather, you can say nucleus. Nucleus is pulling the nuclear, what do we say? Nucleus pulls the electrons towards itself, okay? Besides that, the electrons are revolving, and that's where the Pauli's exclusion principle, no, Pauli's rule comes, exclusion principle, yeah. Revolving means just like the earth revolves around the sun, right? Earth moves around the sun. So same way, they are revolving around the nucleus. And next thing is that they are also spinning on their axis. They are spinning just like the earth. So let me just move it here. So they are spinning on the axis, and just like the earth is doing. So just like earth in solar system. Okay, so they're spinning on the axis. So how are they spinning? One is moving clockwise. This is anti-clockwise, and sorry, this is the anti-clockwise is moving down. So here, so this is anti-clockwise, anti or counterclockwise, and the other one is moving up, and that's the clockwise. So one is counterclockwise and the other is clockwise. So these two electrons, because remember that these electrons are also going to repel. So let's do this here, that there is a positive and positive charges repel, negative and negative charges repel. So that's why the electrons can repel each other too. But positive of the nucleus and negative of the electrons, they attract. There is attraction here. Okay, and that attraction is the nuclear pull. Okay, now this way, the spinning of this thing. Now, how do we prove all this though? We can't see all this. Like I said, the energy, let's see, the only thing is, okay, it's showing like this here, which is a good thing. At least it's to you guys, it's showing like this. Okay. Where is that cat? Here. All right. So they said, okay, now you guys are all of you guys on the Zoom and the students present here. You guys, let's do a thought experiment. Okay, this is a thought experiment. You have to, that's why I'm saying, you have to think in chemistry, you have to think. Okay. How can we prove all this? That the electrons are existing as waves, electrons existing as particles, and then we have all this whole bunch of math, which hardly common people don't even understand. Like even the intelligent people who are in the academia can't understand. And then you are talking about the location of the electron, and he was very certain about the location of the electron, that where are these electrons present? He was 100% sure. You know, that how many electrons are present in which energy level. That is where he had to face a little music from his critiques. Then he said, okay, we are going to set up an experiment. And then basically it is questioning the reality. What do you consider to be real? And what do you consider to be non-real? What would you believe and what do you don't believe? I mean, like I said, math is such a pure science, it can prove a lot of things. But as common human beings, we have to seeing is believing, right? Generally, you see certain things and then you believe. That's a normal human nature. But the problem is that if you can't see, then you still have to believe, then what can you do? So that's why they set up this experiment. So this is a box. Schrodinger put his cat inside the box. On one end, you see on the corner is a trigger. That is a radioactive trigger, which is going to kill the cat. The moment the box is opened, that trigger is attached to the lid of the box. So when you remove that lid, the trigger goes and the cat 100% dies. Okay, that's fine. But he also put inside a box a food which was laced with poison. Okay, now you guys have to tell me, let's start this experiment. 10 o'clock in the morning, when you set this apparatus, this is an apparatus, you set it up. And now comes the question, is the cat alive or is the cat dead? Tell me, what do you think? 10 o'clock, we start the experiment. Think and tell me. Brainstorm. Come on, guys. Say something.
This is the question I asked last time.
Yeah. What do you think?
Well, if it's just starting, then wouldn't it just be alive?
Okay, good. So one point is that if the experiment is just started, yeah, it makes sense. Logic that the cat is alive. Good. Agreed. Okay. 11 o'clock now. 1 hour later, cat alive or dead? Come on, guys. All you guys over there. Hello, 22 students online. Just write down your response or you can unmute and speak also. Everyone has to participate in this. Abby, Abdullah, Ivy, Alexia, Anna, Annie, Brian, Chelsea, David, Heather, Isaac, Jacob, Justin, Mikala, Rohan, Ryan, Sabah, Shaida, Yesenia. Okay, what do you guys think? What do you guys think?
I think the cat might be alive. It's only been about an hour.
Okay, it's only been an hour. So some people are saying dead, some people are saying alive, some people are saying unknown. Okay, let's move because we're not sure. So let's move to like 1 o'clock. Like we all go for lunch and then we come back and say, okay, now what do you think? Is the cat alive or dead?
I mean, isn't the theory that the cat is neither dead nor alive until you open the box, but until you have a sure answer, he can neither be dead or alive?
It can neither be dead or neither be alive till like, you know, some period of time has passed, say, let's say 4 o'clock in the evening. But still, as a human being, okay, just go outside the box. Like, I mean, think outside the box. What could you do to like, can you do something to make sure that, you know, the cat is dead or cat is alive from your side without opening the box? Some clues. Think about some of the clues. What are the clues? Sound, very good, Shaida, very good. So it's a cat. What kind of sound does a cat make? So can you like seriously? I mean, no cat in the world can sit quietly. You know, you agree to that. No matter where they are, they'll always do that mew mew sound. So, so do you think a cat is going to sit quietly in a box just because you have all the scientists in the world are gathered to see like this drama? No way. She is going to scratch the box, right? She's going to do something exactly.
My cat's able to be quiet, or it was able to be quiet.
That is also true. I agree with you. Your cats can remain quiet. Now, my dog, these animals, they have very strong emotions and they express their emotions also very strongly. If they're mad at you, they may just decide to keep quiet. Say, okay, I'll also have some fun. My dog, if I left the house for like some extended period of time, I came back home, he would put his face towards the wall, back towards me, didn't move, didn't shake, didn't wag his tail, didn't he just pretended as if I don't even exist. So the animals have their way of showing anger. And that could be a silent revolt. So like Kenji is saying, like his cats remain quiet. And so, yeah, so maybe neither the cat moves, so we don't, but it may be alive. Right, 100% alive. She may be sitting on like a what do you call, like a strike, hunger strike. I mean, come on. We put a poison in the food. I mean, animals have very strong instinct, right? That breathing instinct. So what is it? She can sniff. Oh, this food looks like something is not right, right? Animals are very smart. So she may decide not to eat the food and may decide not to move. They are very smart, but you don't know. We don't know yet. We don't know, right? We can only make some speculations, right? We can only make some conclusions, but it's hard to determine whether the cat is 100% alive or it has actually died. I mean, poor thing, she must have died of suffocation. She must have, maybe the fumes of the poison, even if she didn't want to eat the food, the fumes of the poison would have already killed her. But there's no way for us to know unless we ourselves open the box and see what happened to the cat. If we open the box, we know 100% she will die. So that's the thing, that these cats, or cat or any animal or anything. So this was a thought experiment. So I wanted to make you guys also think, so which is very good. Many people participated in this, so this is a good thing. So that's the thing, comes back to the structure of atom, and that is that we don't know whether the electron at one point of time will be existing as wave, or at another point of time, or at the same point it is at a part. We don't know. We have no way of determining that yet. At least, now science is advancing. So maybe we can, I think oh, wait 1 second. Most recent discovery, yes, they have determined the wave particle. They were able to find out. There was something I saw, they were able to now determine that at what point of time it is at a wave and what time it is a particle. But we're talking about in olden times. That is why it's called Heisenberg's uncertainty principle. And they had to bring that cat experiment, okay? But quantum mechanics, yeah, this whole thing is quantum mechanics. But now we are going to look at so how did he prove that? So like I said, he came up with his numbers, and these numbers are called the quantum numbers. So, okay, everybody agreed. Okay, fine. We understand electrons exist somewhere around the nucleus in the energy levels, and we don't know if they are existing as waves. We don't know if they're existing as particles. We know it's a dual nature, but we are 100% sure that they are present in the orbitals. That is what the main thing is about the atomic structure and quantum mechanics. So let's look at this. So how did he initially show? Schrodinger and Heisenberg, they showed it as quantum numbers. So quantum numbers. So instead of saying shell, subshell or orbitals or whatever, so these are quantum numbers. Okay. All right. These are quantum numbers are 4 main types. Okay. Set N is the principal quantum number. And this principal quantum number means it's the main one. So principal quantum, and I'm going to just put it here, Q, and like that, quantum number. And this principal quantum number, what does it depict? It depicts the size of the energy level, size, and also the amount of energy that is present in that energy level. So size and energy. So as you increase the, as the value for the n increases, the size also increases, and an energy associated with that energy level also increases. So a more common term these days now we are using is called shell. Energy level, but more commonly we call it as shell. Okay, but older version was orbit. Older, this is the older version. Remember, the structure of atom is also based on the solar system. So that's one piece. Okay, next is, so what are the values of n? So how can you write down what would be the value of n? N, the values could be 1, 2, 3, 4. So it's very simple. That means energy level 1, energy level 2, energy level 3, energy level 4. Or more commonly, we call it shell number 1. These are the shell numbers. Okay. So shell number 1, shell number 2, shell number 3, shell number 4. Simple. Okay. Next, now we are looking inside the shell. What is there inside the shell? Inside the shell, now we know that this is called the L. L is the angular momentum. So what does angular momentum signify? Angular momentum. Any thoughts on that? What would angular momentum specify? So this is also a quantum number. This relates to the shape of that energy level, or inside that, where is it? Remember, we are looking at the place where the electrons are found. So we are looking at the house, we are looking at the room. So that place where the electrons are found is just like a human being found in a city, right? Big city. When you're trying to locate individual, you look at a city, then you look at the street, then you look at the house, then you look at the room, right? And if it's a student, then it's a dormitory, the room number, so forth. Okay, so angular momentum, this thing is in common terms, is the subshell. So subshell is the part of the shell. And what is the value of it? It has the value is the value. So this is, let me just put it here. This is the value. So the value of L is equal to whatever the value of N is 1 less. 1 less than N. So this means 1 less than whatever the value of N is. Okay, that's what it means. Okay, now look at these subshells. Subshells are like, what would be the values in that case? Let's look at this. L, the value of L is equal to 0, 1, 2, 3, 4, and so forth. Okay, so what does 0, 1, 2, 3 signify? This means S, this means P, this means D, and this means F. And we are still working, I'm going to just move here. So what does S, P, D, and F mean? S, P, D, and F. Do you guys know any meanings of these? S, P, and D. Why not A, B, C, D? Why not M, N, O, P? Why not X, Y, Z? It means something. Yeah.
Numbers of electrons. We have it in our handout too.
No, it's not in the handout. I'll write this. I'll write this here. It means S means very sharp. Look at that. They could not see the electrons, but they are saying this is 100% guaranteed. The electron is present here. That guarantee came, yeah, that's the one. That guarantee came through math, that support, that confidence, and principle. That's that place where the electrons are found is like, it's the principal residence or the main residence where the electron is present. It can be anywhere else. It's 100% guarantee he is going to be there. And the location is very sharp. They could see it. For some reason, they could see it. But at the same time, because the electron exists as a wave and a particle also, so it can also be diffused. So sometimes you may be able to see where the electron is, and sometimes it may not be present in that place. And F is fundamental. So every electron has a like a value. Every electron has, it's like that, there's a value, there's an energy associated with that spot, you know. So these are the subshells. So that's the angular momentum. Okay, that's fine. Then comes the ML. ML, what does ML stand for? M is the magnetic quantum number. Magnetic, MAGNETIC, magnetic quantum number. Okay. Yeah. Yeah, go ahead.
So the shell, I know you wrote like 1 through 4 for the original shell and then 1 last. So then would it go all the way to 8 for the value of n, and then L would go all the way up to 7?
Yeah.
Which is just gonna stop out.
Yeah, but you know, the elements that we have up till now, I think we have only been able to reach till the 4th shell.
Okay.
Yeah, the other ones we haven't identified. I mean, there's, see, how do we get these elements? Either continuous discovery, you know, and now obviously they must be in very trace amounts. That is why we haven't been able to locate. We have been able to find only till, not find, actually, I think the ones that are like 118, 117, all these are, which ones are these? See, this is the one. After 108, 109, yeah. After 109, we are certain. But after that, we have manufactured them. 110, 111, 112, 113, 14, 15. So yeah, artificially manufactured them because we all the other ones are found in large amount on this earth. So, or even if it's a trace amount, still they are present, you know, in enough samples that we were able to put them as average, you know, isotopic masses here. But the ones from 110 and above, they I think we have only been able to reach till 3rd or 4th shell, if I'm not mistaken. Wait 1 second. Energy levels, 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7. No, 7. We have been able to reach till 7. Yeah, 7 energy levels. But 8th and above is like we'll have to manufacture. Or if a meteor strikes from outside and falls on this earth and it's just bringing in a totally new element, then yeah, you know, we have it. But anyway, so magnetic quantum numbers. Okay, magnetic quantum numbers, what do they tell you? These determine the orientation of the orbitals. Orientation in 3D. Orientation. So here's a very important part. Orientation means that here we are bringing in like 3D model. In 3D, where are the electrons now? Length, width, and height. We guys know it. Everything that we find on this earth, or for us, length, width, height, all these, like the vertical, horizontal, and diagonal, these are the areas or the space in our dimensions that we are able to locate objects. So same thing we're trying to figure out. So with that said, the interesting thing is that the structure of the atom is not in 3D, or not 2D. It is like this. So this is the nucleus. And all around the nucleus, so this is the nucleus, all around the nucleus are these let me put this here, are these energy levels which are like overlapping. This is another piece, these energy levels. So this is a 3D model of electron, of an atom. This is a 3D model. So 3D model is like a ball or a sphere, you know. So 3D model of an atom, and this is like a ball. Just like you hold a ball and then you can tell, like, this is how high the ball moves, or this much space the ball is occupying, or how fat the ball is, you know, so those things. So that 3D ball or sphere, that is how the atoms look like. But anyways, let's look at the magnetic and what are the values. So magnetic quantum numbers are actually the orbitals. That's the real ones. Magnetic, okay, orbitals. And here we will see then what would be the values of these. The values are +1. These are the values are, sorry, -L, comma 0 plus L. Okay, so here's the thing. When, look at all these values. When so these are the values of ML. All the ML values are 3 ML values. So pay attention to this thing here. When L is equal to 0, then ML, the magnetic quantum number ML, is equal to 0. When L is equal to 1, then ML is equal to +1, 0, -1. Okay, when L, which is the angular momentum or the subshell, is 2, then ML is equal to sorry, this should be minus. Start with minus and then go minus, -1, 0, +1. Then this becomes -2, -1, 0, +1, and +2. Okay, so minus and minus means like it's closer to the nucleus. Minus means that. Okay, when L is equal to 3, then the values for ML would be -3, -2, -1, 0, +1, +2, and +3. Okay, so that's what the, so whatever the values of L are, you just have to put plus minus and then you have to put 0. Okay, and then the last one is the MS. So he said, so this is all basically describing the electrons. So MS is the spin quantum number. Spin, the spin quantum numbers are basically, you know, basically, as the name says, spin of the electrons, whether it is clockwise or it's anti-clockwise, so, or counterclockwise. So clockwise would be +½ and counterclockwise or anti-clockwise is minus, is equal to -½ Okay, so two of these, these things. So now let's look at, okay, now let's start looking at these problems and we will do this. I'm going to do one big one for you and then you guys can go from there. But let's look at this. N, L, the name, then comes the M, number of orbitals, and number of electrons. Okay, so actually, just need more space here. Okay. All right, so let's do this. These values. If the value of n is 1, that means we are looking at the first energy level. The first energy level. So what would be the value of L? Just now based on what we covered. Yeah, you're right. It looks like, okay, so here's another thing. The 0 does not mean nothing. 0 is just a numerical value. It still means something, okay? So here, let me put this here. So whatever the value of n is, L is going to be 1 minus n, okay? And whatever the, so in other words, this is the, let's just put this here. This is the shell, and this is the subshell, and then M, N, L, and then the values of L, M is plus, is minus 1, minus 1, 0, plus 1, sorry, or not 1, sorry. It is the value of N is minus L, 0, plus L. So do that. Number of orbitals and the number of electrons. So that's one piece. So this is N minus 1. All right. So if the value of the first energy level is 1, then the value of L is 0. Okay. And what would be the value of M? So if it is 0, then the value of M also becomes 0. Okay. But how many number of orbitals means how many orbitals are there? How many? How many? Number of orbitals means that. How many orbitals? So how many orbitals are there? Like I said, 0 does not mean that there's nothing. That means there's something. 1. Okay. So this is actual name is 1s. So the name of the orbital is 1s. So the number of orbitals, and I will change this also. Let's get this here. Number of orbitals, how many, and name of orbitals. Name of the orbital. And then comes the number of electrons, the total number of electrons. Okay, now let's do this here. So number of the first energy level, the L value is 0, the name is 1s, M is like 0, the number of orbitals is just 1, the name of the orbital and the subshell name is the same. And in the s orbital, a maximum of 2 electrons can be accommodated. Okay, keep that in mind. Next, if the energy level is 2, what is the value of L? 1 and remember it's n minus 1. So it's 0 and 1. Okay, 0 and 1. The name is 2s and 2p. What are the values of M? So if it is 0, so it is going to be the value of M is also 0. But if the value of L is 1, what is the value of M? Very good. Minus 1, 0, and plus 1. Remember the P has 3 orbitals. You guys have studied that in the previous classes. So number of orbitals is 1. Here, how many orbitals do you see? How many orbitals? 1, 2, and 3. So how many orbitals do you see? 3 orbitals. Very good. So these 3 orbitals, okay? So the name is 2s and 2p. How many electrons? So remember that. Let me put this here. Every orbital, every orbital, or one orbital rather, one orbital can hold a maximum of 2 electrons. Okay, so with that said, s orbital will hold 2 electrons, p orbital holds 6 electrons, d orbital holds 10 electrons, and f orbital holds 14 electrons. Okay, then s subshell has 1 orbital. P subshell has 3 orbitals. D subshell has 5 orbitals. And F subshell has 7 orbitals. So we will look at that now. Okay, so S can hold a maximum of 2 electrons. P can hold a maximum of 6 electrons. Okay, so in mathematically, he proved that. Okay, then comes if n is equal to 3, then what's the value of L? Yeah, 0, 1, and 2. Okay, so if L is equal to 3, then if n is equal to 3, then these are the values. So what are their names? This is 3s, this is 3p, this is 3d. Now look at that. M, what is the value of M for every time it is n is equal to 0, L is equal to 0, and so if, L is equal to 0, M is also equal to 0. Number of orbitals is 1, the name is going to be 3s, and there are 2 electrons here. Next, 3p, when it is 1. So the name, so how many, what's the value of M? Just related to this. So focus on these numbers. And these guys relate to that. So 3p. So in other words, if the value of L is 1, what is the value of M? Don't forget these guys on top. Minus 0 plus those values. So it is going to be minus 1, 0 plus 1. Okay, so the number of orbitals are 3. These are 3 orbitals, 1, 2, 3. So the name is 3p. Anytime you have 3 orbitals, 3 orbitals. 3 orbitals is p. So, and how many electrons? 6 electrons can be held. D, there are 2. L is equal to 2. So the value of M is equal to minus 2, minus 1, 0, plus 1, and plus 2. Okay. And how many orbitals do you see now? 1, 2, 3, 4, 5. Very good. So 5 orbitals. What is the name? 3D. Very good. Excellent. And how many electrons? In D, 10, 2 in each, right? Okay, now let's do 4 also. 4. So what should I put now? Now you get to see a pattern. So what should I put here for L? Heath? Name. 0, 1, 2, and 3. Very good. So the name is 3s, 3p, sorry, 4s, sorry. Yeah, 4s, 4s, 4p, 4d, and 4f. Okay, 4s. Now, when the value of L is 0, the M is also 0. Number of orbitals is 1, and that name is 4s, and there are 2 electrons here. Okay, next. When the value of L is 1, what is the value of M? It's basically the same thing, repeating from the top. Very good. So negative 1, 0, and positive 1. So how many orbitals are there? 3 orbitals. Very good. Name? 4p. Very good. Number of electrons? 6 electrons. Good. Now 4d. When the value of L is equal to 2, what is the value of M? Yeah, same thing as you see on the top. -2, -1, 0, +1, +2, and that's it. So how many orbitals are there? You can clearly count 1, 2, 3, 4, 5. These guys were 3 orbitals. Okay, and so the name is 4D. And the electrons are how many? 10. D can hold a maximum of 10. Okay, what about F? This guy. Very good. -3, -2, -1, 0, +1, +2. It's very important to put plus. Don't just assume that it's positive. Okay, so now how many orbitals are there? 1, 2, 3, 4, 5, 6, 7. 7 orbitals. What are there? This is 4F. And each orbital can hold a maximum of, no, each orbital holds 2. So a total becomes 14 electrons. Okay, now if you look at this here, energy level 1 can hold how many maximum electrons? 2. Energy level 2 can hold a maximum of how many electrons? No. Look at the bracket I made. Maximum. All, you have to combine all of it. All of this. So what is that? 8. Maximum electrons that can go in the second energy level is 8. You see that? The less the electrons are being held, you know, the energy level is like lower energy level. Higher the energy level, the more space it has to keep the electrons. So more electrons can be accommodated. Now look at this guy. How many electrons can come here? 18 electrons. And the last one, 4th energy level. How many total electrons? Not valence, but 32. Yes. So the last one, the 4th energy level is huge. Huge. So it can accommodate 32 electrons. But here's a problem. The problem is that because of this structure, it is not so linear. It's not so nice, as you can see here. Okay, so it is like they overlap. Okay, let's look at some problems. Let's see. What time is it now? Okay, I want to just finish off the theoretical pieces here first, and then we can go ahead and do the actual problems later. Because the important piece in this chapter is more like electronic configuration is more important. And yeah, understanding these theoreticals. Okay, here are a few things here. And I'll give you a little cheat sheet. The cheat sheet is that, and you can see for yourself also. And some of these tricks to remember. These are the tricks to remember. And it really works very well. Now I'll tell you what. N square is equal to the total number of orbitals. And you can see for yourself. If the value of example, so here's an example. If the value of N is equal to 3, so what is 3 square? 3 3s are 9, and there are 9 orbitals. And we can go back and okay, 9 orbitals. Okay, where are these 9 orbitals? If you look at the value of 3, where are those 9 orbitals? You see that? Let me put this in a lighter color. Or 9 orbitals. So these are the orbitals, 9. So here is this 5 plus 3, 8, plus 1, 9 orbitals. So this relates to this 3. So this is one thing, you know, you can check in case you're like lost, or in case you have a question comes that, you know, what is, find the number of orbitals if N is equal to 3, then, you know, you can get it from there. Okay, this is one piece. Next is this is one. Next is the, if you have the maximum number of electrons present in an energy level. So maximum number of electrons present in energy level are what? It is, the rule is 2 times n square. And you can see that if example, let's do this. If example is equal to same thing, if n is equal to 3, then 2 times 3 square is what? 2 times 3 3s are 9, and that is 18. So 18 electrons are present in, and you can see that if n is equal to 3 back here, if n is equal to 3, how many electrons do you see here? 18 electrons. So that's another way, you can use these little tricks. These are not in your book, but okay, let's look at this one. Degenerate orbitals means that they are the same energy level. So degenerate orbitals have the same energy. So this means like all the p orbitals, wherever they are in the atoms, they will all have the more or less the same, energy. So there are 3 of them. So the three orbitals in p. So the same energy d orbitals, all of them have the same energy. So there are 3 orbitals present in p, 5 orbitals present in d, and f orbitals again, same energy, and there are all 7 of them have the same energy. Okay, so how do we know this mathematically? How did they determine this? So this is the 2 degeneracy is like, how did they determine how many orbitals have the same? So this is 2l plus 1. That means whatever the value of L is, right? So here, let's do this. So for example, you have 4p. 4p has how many? So 4p is 2 times the value of L. So in other words, wait one second. So this 4p means that n, the value of n is equal to 4. Okay, n is equal to 4. So when n is equal to 4, then the value of L is equal to like 3. So in other words, it is what is that? L is n minus 1, 0, 1, 2, and 3. Okay, and the ml values are going to be 0. This one is minus 1, 0 plus 1. This one is minus 2, minus 1, 0 plus 1 plus 2. This one is minus 3, minus 2, minus 1, 0 plus 1 plus 2 and plus 3. Okay, so now okay, so this would be this thing. So specifically for 4p, if the question is asking you this, so this means for 4p, how many degenerate orbitals are there? So specifically for 4p, so 2 times L, the value of L is equal to one second. So we have to stop somewhere. Wait one second. Oh yeah. 2L, 2 times L plus 1. So think these are all quantum numbers that are associated with just the when n is equal to 4. But for 4p, you stop here. And 1 second, 2. Oh, yeah, that's what it means. L plus 1. So 2 times the L is 1. L stands for 1. I'm looking at the other values. So n and plus 1. So that is 2 times 1 plus 1 is 3. So 4p has 3 degenerate orbitals. Okay. All right. So that's degenerate means same. So same is the case you can get for 5D. Let's look at this example, 5D. So you have to look at the value of L. So N is equal to 5, right? And L is equal to 0, 1, 2, or let's put it the other way around. 0, 1, 2, 3, 4. Okay. Now, so for 5D would be 2L plus 1. So 2 times L is, 1 second, SPD. Yeah, you will have to put it, I think you will have to put it as S. Let me put this in red. It becomes clear. So this would be S, this is P, this is D, and this is F. So here, this is S, this is P, this is D, and this is F. And that the last one is G actually. 4 is G. So we are talking about 5D. We are looking at 5D. So that means you will stop here. Stop here. So the value of L is equal to 2. So L is equal to 2 plus 1. So 4 plus 1 is equal to 5. So 5 degenerate orbitals. So 4D is made up of 5 orbitals that have the same energy. Okay, so this is how they were able to determine. I mean, I don't know how they I mean, there's more math to it, but nodes, radial nodes. Okay, we'll just leave it at that. So what I have shown you, oh, there's something else also which we forgot to do here. Just keep this in mind because it takes so much space. So here, these 2 orbitals, their energy, their spin is like that. So 2 orbitals, their spin is like that. For the 3 ones, it's clockwise, anti-clockwise, clockwise, anti-clockwise, and clockwise, anti-clockwise. For the 6, okay? And then 2 is always like this. The 6 is going like in orbitals, like that. And 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Okay, so you will be asked to draw all the quantum numbers. So this is what you will do. So, you know, I think it's fairly simple. You can just, once you start doing it, you will know it. But okay, next is few last pieces here. Okay, yeah, from here only, let's do this question. If the question is asked, when n is equal to when n is equal to 4, then find the number of electrons. So, you know, you will have to do all of these, write down all of these, and write all the quantum numbers basically. So the main quantum numbers are these guys. These are the quantum numbers: N, L, ML. This is actually ML, and this is the ms, the spin. So these will be, you have to do these. Okay. So if the question is find, yes, that's the question. So if the, let me just copy this from here so I don't have to write this again. Copy. Okay, so now the question is that in okay, if the, this is what was, did I do this here? N M, this is L, this is ML, and then MS is the spin. Okay, so if the question is asking you find the, for if n is equal to 4, n is equal to 4, find the quantum numbers that have +1, ml is equal to, or the angular momentum is equal to +1. Find how many electrons have that. So you are going to look at, now after writing all this, you're going to look at, okay, n is equal to 4, you have all these 4, and you're going to look at, okay, this guy's +1 is 1 electron, second electron, and third electron. So 3 electrons have +1 quantum number. Okay. If they're saying, okay, find if n is equal to 4, n is equal to 4, find how many electrons have L is equal to 2. How many electrons have L is equal to 2? How many do you see? So here is your n is equal to 4. Then you go L is equal to 2. And in L2, you see 2 electrons here, 2 here, 2 here, 2 here, and 2 here. So how many are there? How many? 10. Very good. So 10 electrons have n is equal to 4 and L is equal to 2. So these type of questions, okay? So if the questions are like, how many electrons? Yeah, if n is equal to 4, very interesting question. If n is equal to 4, ms is equal to minus half. How many of them have minus half? So remember that these are here. This is plus half and minus half. And that is like that. Okay, then this would be plus half, minus half, plus half, minus half, plus half, and minus half, and so forth, you know, and then you just, you know, carry on through that. So this would be for the 10 electrons also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14. So now you tell me how many have minus half? Very good. So a total electrons we had here were 32 electrons. Total was 32 electrons total, but they are plus half and minus half. So the ms, so half of them would have half of 32. Half of 32, that is 16 electrons will have the half, minus half, or would be moving counterclockwise. All right, guys. So this is one thing, and let's just finish this polys because I want to start off with the electronic configuration next time when you guys come. So let's just finish this quickly. One thing is the penetration effect. It's very interesting, penetration effect. Let's finish this. Penetration, penetration effect. So it is the effect of the nucleus. The nucleus. So here is the nucleus, the eye of the nucleus. Just imagine that here is the eye of the nucleus, and this nucleus is observing. Okay, the nucleus is observing the electrons, keeping an eye on the electrons. So at one point of time, the nucleus is going to see the electrons, like the electrons more, the s electrons, the electrons that are present in the s are going to be seen more by the nucleus. So this is 2s. So 2s electrons are being seen more by the nucleus, therefore it has more control over them. But the 2p he sees, yes, but it gets shielded. So once in a while it sees the 2p, but then it becomes shielded by 2s. So 2p it's able to see only once. You see that? So if the nucleus is looking at the electrons, to the electrons that are in 2s, electrons are being seen by the nucleus more. Okay, more. So they are more in control of the nucleus. So the nuclear, therefore, nuclear pull is more. Nuclear pull is more. Okay, but 2p electrons are shielded, and we will cover the shielding more, are shielded by the electrons in 2s, 2s electrons. Therefore, nucleus only sees 2p electrons, occasionally or less. How do I? Like anyway, when they're coming closer. So therefore, nuclear pull is lesser on 2p. So nuclear pull less on 2p electrons. Okay, and then same goes with 3D. Look at this 3D situation. It's very beautifully explained in this, chart. So here is the scenario with the, okay. What is this? This is the distance from the nucleus. Distance from the nucleus. The further away the electrons go from the nucleus, distance from the nucleus. And this is the radial probability of looking at the electrons from the radius. So radial probability, Probability. Okay, so here's again is the nucleus, and he's looking at the 3D. Now look at 3D. So yeah, it is going to look at 3s more. So one time, second time, and then remember these electrons are moving, and then the third time. When the 3s goes, the 3s orbital, the 3s electrons are going a little bit further away, regardless, they are seen more by the nucleus. Then comes the 3p. 3p is only seen a little bit, and then 3s comes in between, and then the 3p gets shielded by 3s. So the 3p is very little. Now comes the 3D. Oh my God, 3D is just very little. The smaller the hump, little bit, just a little bit, and that's the end of it. So 3D is the least. So this is how they determine the energies. So 3s, lower energy than 3p. 3p, higher energy than 3s, but lower than 3D. So the lowest energy was of, wait 1 second. The highest energy was of 3D. Highest energy because it has the lowest nuclear pull. Because nucleus is unable to see it. That's why. And 3s is the lowest energy, because nucleus keeps, like like a father or a mother, they keep looking at their children, keeping an eye on them, micromanaging them, those things. So the further away, in other words, an electron goes from the nucleus, the more energy it gets, but less nuclear pull. Okay, so we will discuss this more, and that defines the behavior and everything about the atoms, but we'll discuss this more. So I'm going to stop recording, and anyone has any quick